This is section 13.2, part B. We'll continue to set up and evaluate some double integrals. And in example 2, we're being asked to integrate the function 4y dA over the region R bounded by a couple of specific functions. So I'm going to start by getting a picture of this. You can use your calculator, of course, to generate graphs as well, but these aren't too bad, so I'm just going to sketch them by hand. Y equals x squared, and y equals x plus 6. Just going to have a y-intercept of 6 here. All right, so we are looking at a region, R, that looks like this. And once again, I don't see any particular reason not to go with vertical rectangles. If I were to draw my vertical rectangle anywhere in this region, the bottom of the rectangle would always be on the parabola, and the top would always be on the line. So I have consistency. Setting up my double integral, again, my integration is, or my integrand is 4y. And then I'm going to be doing dy first, since I'm integrating my rectangle between two y equals values. And that leaves dx for second. I always go bottom to top. The bottom of my rectangle is on the y equals x squared curve. The top of my rectangle is on the line, where y is equal to x plus 6. I do need to find the intersection points to get the x values for my limits of integration. And again, you can either graph on your calculator and get the intersection points that way, or we can simply set the two equations equal to one another. Doesn't look like they're going to be too bad to solve this time. I can factor that. X minus 3, x plus 2, giving me values of positive 3 and negative 2 for x. So my limits of integration on x go from negative 2 to positive 3. All right, we're all set up. So let's go ahead and do our integration. The integral of 4y with respect to y would be 2y squared. And that goes from y equals x squared to y equals x plus 6. Using my fundamental theorem of calculus, I plug in my upper limit of integration first. So 2 times x plus 6 squared. Subtract 2 times, it's really x squared squared. And you can plug that into your calculator just like that. I'm probably going to put that in as x to the 4th, but other than that, I'll plug it in just like that. And I actually did this ahead of time this time. Let's see, I got 1,000 over 3 as the value of that integral using technology. All right, in example 3, we once again have a double integral. Our integrand is given and the region R is described. So let's start by sketching the region. I'm going from y equals, or excuse me, my region's bounded by y equals the square root of x. And y equals x minus 2. So a line with y-intercept of negative 2. And y equals 0, which is the x-axis, meaning that my region this time looks like this. Now notice this time, if I tried to draw vertical rectangles, it would probably be a mistake. Or at least it would take me more work to do something that I don't need to work quite so hard for. The reason vertical rectangles are not a great choice is over here, my rectangle would start on the axis and end on the curve y equals the square root of x. But over here, the rectangle would start on my line, y equals x minus 2, and end on the curve. That would mean that to actually set this up with vertical rectangles, I'd have to set up 2 double integrals, and I'd rather avoid that. Instead, if I draw my rectangles horizontally, notice that no matter where I draw them through this region, they always start on the square root curve and end on the line. So that's going to be a better choice. It's going to allow me to do the problem more efficiently. Now, as soon as I've drawn horizontal rectangles, I do have to change the way I think about my equations. These now have to be x equals equations, since I'll be going from left to right. Those are x values. So I'll change this first one to x equals y squared. And solving for x in the other equation, x would equal y plus 2. All right, I'm going to begin setting up my double integral. My integrand is 2xy squared. And this time, since I'm going horizontally, I'm integrating from an x value to an x value first. So I'll start with dx, and I'll do dy second. Going left to right, the left side of my rectangle is on the curve x equals y squared, and the right side is on x equals y plus 2. As far as y values, clearly I'm going to start at y equals 0, but I'll need this intersection point to figure out the y value for the upper limit of integration. And once again, you can either get that off of a graph on your calculator, or you can set your equations equal to one another. And solving that one, I'll factor it, which gives me y equals 2 or y equals negative 1. Clearly the one I want is the 2. Negative 1's not part of my region, so I can ignore that. All right, our integral is all set up. So let's go ahead and do our integration. My integrand, 2xy squared, integrating dx. Integral of 2x would be x squared, multiplied by the constant y squared. And that gets evaluated from x equals y squared to x equals y plus 2. Plugging in the x equals y plus 2, I would have y plus 2 squared times y squared. Subtract, plugging in x equals y squared, I'd have y squared squared times y squared. I'm going to simplify just a little. What I actually have is y squared times y plus 2 squared. And that would be y to the 4th times y squared, or y to the 6th. I went ahead again and pre-did this integral. It did convert to a fraction. It was not a very nice fraction this time, 1552 over 105, or approximately 14.781. All right. Hopefully you're starting to feel fairly comfortable with the actual process of evaluating these integrals. But the setup, we probably could stand to do a few more practice problems with. And so these next few examples, we're going to set up some integrals just to get practice with that, but we won't actually evaluate them. In fact, if you'll notice on the next page, I haven't even given you functions to integrate. I've just set up the integral for a generic function, f of x and y. So example 4, our region is this triangle. Our vertices are 0, 0, 0, 3, and 4, 2. And so here is my region. All right, I want to think my big decision at the beginning of any of these problems is whether I should use horizontal or vertical rectangles. And in this case, I'm thinking vertical. Horizontal would always start on the y-axis, but sometimes it would go to this top line, other times it would go to the bottom line. So that's not consistent. A vertical rectangle will always go from bottom line to top line, no matter where I draw it. I will need the equations of these lines, and so let's take a look at those next. We can get these just by thinking about the points themselves. Let's see, this was the point 4, 2, and this of course is 0, 3, 0, 0. So this first line here has a slope of, let's see, what are we doing? Up 2 and over 4, so 2/4 or 1/2 would be our slope. This equation would be y equals 1/2 x plus 0, since the y-intercept is 0. And on this equation, my slope goes down 1 and over 4, so a slope of negative 1/4, and then a y-intercept of 3. So when I integrate my kind of generic function f of x and y here, doing a vertical rectangle means I'm going from a lower y to an upper y, doing dy first, leaving dx for second. My lower limit of integration is 1/2 x, and my upper limit of integration would be negative 1/4 x plus 3. We don't have to work too hard for the x values this time. X clearly starts at 0 here. And then this x equals 4 is where everything ends. So I'll stop when I get to 4. And if I actually had a function, this is where I could begin to evaluate. All right, in example 5, we're looking at the region inside the circle, x squared plus y squared equals 25, and then to the right of that line. So there's my circle of radius 5. And this line would have a y-intercept of 5 and a slope of negative 3, so a fairly steep slope here. So I'm looking at this region, inside the circle and to the right of the line. Okay, first of all, let's decide about our rectangles, vertical or horizontal. And I'm thinking horizontal this time. Vertical rectangles sometimes would go from the line to the circle, but over here they would go from the lower part of the circle to the upper part, which is not consistent. So I'm going to go horizontal, and that way I can always go, no matter where I look, from the line to the circle. Since I am going left to right, I'll need my equations solved for x. So let's start with this first one. The circle itself, solving that for x, I would have 25 minus y squared, and then I would have to take the square root of that. I did choose the positive square root because for my region, all of these x values are on the positive side. As far as the line, let's see, if I take this equation and solve it for x, I would have y minus 5, and then I would have to divide by that negative 3. And that's good enough. I don't really have to simplify any further. So, my function f of x and y, whatever it is, with horizontal rectangles, I am going dx first, left to right, followed by dy. And the left side of my rectangle is on the line. So my lower limit of integration, y minus 5 divided by negative 3. The right side is on the circle, where x is equal to the square root of 25 minus y squared. All right, I do need the limits of integration on y. The upper limit's no problem. We can see it right here. It's 5. But this lower limit, I'm going to have to figure out. That's where the line and the circle intersect. And in this particular case, I could set these equal to one another, but the algebra on this one is quite a bit more complicated. So I'm going to suggest that on this one, you really do simply use your calculator to figure that out. If you just on your calculator graph these two equations and look for the intersection point, let's see if I can get this visible here. I'd have the square root of 25. Excuse me, we can't do that in here. We could do it on Desmos. You know what? That might actually be a better choice. Let me see if I can bring up a Desmos screen. Pardon me for a moment. I'm still kind of getting ready or getting used to this as well. And I will try and get a little better at the technology as we go. But I'm going to do this on Desmos so that I don't have to worry about the fact that I've got functions that are solved for x instead of y. So I'd have x equals the square root of 25 minus y squared. And then I've also got x equals y minus 5 divided by negative 3. I'll probably put that in parentheses. All right, and at this stage I can go right over here and just click on that point, and I can see that the intersection point is at 3, negative 4. So that y value that I'm looking for is actually this negative 4 here. And there would be the setup for my integral. All right, let's do one more. On this last one, r is bounded by y equals the absolute value of x, and y equals 4. So there's my absolute value graph. And on the horizontal line, y equals 4. So let's see here. As we start to think about our double integral, our first question again is going to be, do I want to do dx or dy first? And in this case, I think I'm going to go back to a vertical rectangle. No matter where I draw my rectangle, the bottom is always on the absolute value graph, and the top is always on y equals 4. So going dy first, followed by dx. My lower limit of integration would be the absolute value of x, and my upper limit would be 4. As far as the intersection points here, once again, you can certainly use a calculator or a computer to calculate those, but if I were to set these equal to one another, the absolute value of x is equal to 4, x is going to be plus or minus 4. And so there's the setup of my integral. All right, we'll pause there and come back and we'll continue this section in the next video.